Hello, everyone. I hope everyone is doing well today and is looking forward to the seminar. Walter may not be able to join us today, just as a heads up. And today we'll be hearing from Dr. Kevin Boldt. Dr. Boldt is currently an assistant professor in kinesiology at Trent University. Dr. Boldt completed his bachelor's, master's, and PhD at the University of Calgary in the kinesiology department. Dr. Walter Erzog supervised his master's and PhD research. Dr. Boldt's research interests include understanding how the body adapts to exercise and dietary stimuli, and mechanisms of exercise and sport performance. After completing his doctoral training, Dr. Boldt was a sessional instructor at Western University and the University of Ottawa. In July of this year, Dr. Boldt began his current position as an assistant professor at Trent University. Kevin has several proud scientific accomplishments, such as being invited to write a special commentary after his paper was highlighted by the American College of Sports Medicine. And he recently released his book titled Superhero Physiology. As a fun fact, Kevin has a 4-year-old daughter, and him and his wife are expecting a second next month. As a reminder, I'll first turn it over to Dr. Boldt for his presentation, and then we will have a question and answer period to follow. And at that time, I'll remind everyone how to submit a question. So with that, Dr. Boldt, you're welcome to start screen sharing and begin your presentation whenever.
Great, thank you, Emily. Can everybody see the screen?
Looks great.
Properly? Yeah, sweet. Okay, cool. Well, thank you for the introduction. Like Emily mentioned, I did all of my training in Calgary, so it's nice to, I guess, be back as far as we are back. Cool. So the health and the function of the heart have been shown to be adaptable. With factors such as aging or with obesity, it results in a decreased function or decreased health of the heart. Conversely, behaviors such as exercise will lead to an increased function of the heart. And the focus of today will be looking at the mechanisms of what actually leads to those increased or decreased functions. So what the mechanical factors are that might lead to a decrease or an increase in function in response to things like obesity or different types of exercise training. So to start, we'll focus on the obesity side of things, looking at what exactly is changing with obesity at the mechanical level of the heart. So with obesity, individuals who have obesity with a body mass index greater than 35 kilograms per meter squared have a 2 to 3-fold greater risk of death at any given point. So that the risk of dying from all-cause mortality is increased with a BMI greater than 35. Specifically, each 5 kilogram per meter squared increase in BMI results in a 30% increase in cardiovascular disease mortality risk, so the risk of dying from cardiovascular disease. And so the first background study I'll quickly talk about, wanted to investigate what the mechanical mechanisms might be that would lead to that increased risk of death or increased risk of cardiovascular disease. And so working with Jacqueline Rios, who I think actually might be watching today, we collaborated on a study which looked at to evaluate the mechanical adaptations of the cardiac muscle in response to obesity. And so we had 12-week-old Sprague Dawley rats, and they were consumed either a chow diet or a high-fat, high-sucrose diet, which is our typical obesogenic diet. The chow diet consisted of 25% protein, 5% of the calories came from fat, and then 50% carbohydrates. And importantly, of those 50% carbohydrates, 3% of them were sourced from sucrose. And then the remainder of the bulk came from fiber and moisture. So a pretty typical diet. This is a very standard chow diet for rats. And the high-fat, high-sucrose diet, or the animals in the obesogenic diet, consumed a diet that contained 20% protein, 20% fat, 50% carbohydrates. But again, importantly, of that 50% carbohydrates, 97% of it was sourced from sucrose, so very high in sucrose. And then the remainder came from fiber and moisture. So the primary differences to the diet was the fat content going from 5% to 20%, the source of the carbohydrates being primarily from sucrose in the high-fat, high-sucrose diet, and then the remainder of that being made up from fiber and moisture. And these animals spent 24 weeks on the diet. At the end of the dietary intervention, we did mechanical testing on the heart muscle itself. So we took strips of muscle. I'll talk about the mechanical testing in detail a little bit later on, but just very briefly, a strip of muscle was suspended between two hooks. On one end, the hook was attached to a length controller, which allowed us to change the length or the position of the muscle itself, how much it was stretched. And then the other side, the hook was connected to a force transducer. So it allowed us to control the length of the sample, as well as measuring the force output that the muscle had at any given time. And again, I'll talk about all the specific tests and how we did those tests later on. But for the background study, we compared the active force the muscle could produce, how fast it could shorten, as well as its sensitivity to calcium. So those were our mechanical function variables. When we compared the obese animals to the chow-fed animals, there were no change in the active force production of the heart muscle. So there's no difference in the amount of force the muscle could produce. There's also no change in the sensitivity of the muscle to being activated by calcium. So it activated just as well. However, there was a lower shortening velocity. So it allowed to shorten unimpeded. The muscle from hearts from animals who had the obesogenic diet had a lower shortening velocity. So the muscle itself was slower. And these data were previously published in 2020. So overall, the obesity led to a decrease in the shortening velocity, but didn't really impact the active force properties of the muscle. And so we think that decrease in shortening velocity is at least partly responsible for some of the increases in cardiovascular disease risks that is seen. We then looked at childhood obesity. And so there's good evidence that childhood obesity is associated with a greater rate of death during adulthood at any given age point, so earlier onset of death. And there's a twofold greater risk of mortality from cardiovascular disease in those who are overweight as children. And so even controlling for adulthood weight or adulthood BMI, those who were overweight or obese as children, even if they grow up to be a healthy or a lower weight or a lower BMI, they still had a twofold greater risk of mortality. And so the exposure to obesity during childhood predisposed individuals to a greater risk of cardiovascular disease. And again, we want to get at what some of those mechanisms might be. And so the second background study I'll talk about was in conjunction with Graham McDonald. And the purpose of that study was to evaluate the mechanical adaptations of cardiac muscle to childhood obesity. So it's animals who are exposed to obesity during childhood and adolescence or juvenile rats. So we took 3-week-old Sprague-Dawley rats. In the previous study, we had 12-week-old. This study is now looking at 3-year-old rats, so it's much younger. And again, they consumed the chow diet and the high-fat, high-sucrose diet. And those are the same diets that we talked about in the first study. So the 5% fat versus 20% fat, and then the much larger proportion coming from sucrose of the carbohydrates. In this case, the animals were on the diet for 14 weeks. So from age 3 weeks up to 17 weeks, these animals were on the high-fat, high-sucrose diet. And again, we looked at the mechanical properties of the heart, and we specifically looked at the active force, the shortening velocity, and the sensitivity of that muscle to calcium. Similar to the older animals, there's no change in the active force production, so that the active force production of the muscle was not impacted, but there was a decreased shortening velocity and a decrease in the sensitivity of the muscle to calcium. So when exposed at a younger age, there were decreases in both the shortening velocity and the calcium sensitivity compared to chow-fed normal weight animals. And again, this is published in a separate study. So certainly with obesity, there's a decreased function, and we attribute part of that decreased function to the mechanical properties of the shortening velocity and the calcium sensitivity. And so next we want to focus on exercise and increasing the functions. Now we understand a little bit of what's going on with the decreased function. We want to then look at ways we could increase the function and how exactly that would come about. And so we want to look at with exercise training, how that impacted the function of the heart. And so if we imagine the heart as a little schematic, So from a structural perspective, if we imagine in blue, we have the thickness of the muscular walls, and in red, we have the volume of the heart. So this is sort of a schematic of the overall heart structure. If we look at the structural adaptation to different types of exercise, so in this case, comparing resistance training to aerobic training, we see very distinct structural adaptations that occur. And so with resistance training, we see a pretty big increase in the thickness of the muscular walls, but there's preserved ventricular volume. So the volume doesn't adapt, but the walls become thicker, and the ability to produce pressure becomes greater. With aerobic exercise training, we typically will see a proportional increase in the wall thickness, as well as an increase in the volume of the heart. And so the heart chamber is both bigger, and the walls are then thicker and better able to support that greater volume. And there's some controversy in these exact adaptations, but generally they're relatively well accepted as the adaptations to aerobic and resistance training. On the mechanical side of things, there's some evidence about aerobic training. And so if we compare active force, there's generally no change in the active force that it can be produced following aerobic exercise training. But there's an increase in both shortening velocity and calcium sensitivity. And so previously, both shortening velocity and calcium sensitivity have been shown to be increased by aerobic exercise training. However, it's not or wasn't known how the cardiac muscle adapted to resistance exercise training. And in particular, it wasn't known how the muscle adapted in response to a combination. So if individuals participate in both aerobic and resistance exercise training, how the heart muscle is adapted in response to the combined modalities. And so because we do see distinct differences in the structural adaptation to different modalities, we suspect there might be also mechanical adaptations. So the purpose of the study was to compare the contractile properties of the cardiac muscle following either chronic aerobic, resistance, or combination of the two exercise trainings using rats again. And we hypothesized that the differences in the structure that had previously observed would coincide with differences in mechanical adaptation as well. So for this study, we had some additional measures we took. So we looked at the training adaptations. So we wanted to measure whether or not the training is actually being successful. So we did a maximal treadmill test, which I'll talk about in more detail. And we also compared the maximum load that the resistance trained animals were able to carry over the course of the training period. To look at the structural variables, we use echocardiography, so the ultrasound images of the heart to get the structure of it. And then for mechanical testing, we did the same mechanical measures, looking at the maximum force output, the maximum shortening velocity, and the overall sensitivity of the heart muscle to calcium activation. So for this study, we took 3-month-old Sprague Dawley rats, and they were grouped into either a control group, so a sedentary group, an aerobic exercise group. So the aerobic exercise animals ran on a treadmill. There was a flat treadmill, and they ran at 25 meters per minute, and they did so 60 minutes a day for 5 days a week. So every day of the week, they ran 60 minutes a day and had the weekends to recover. The resistance exercise training group utilized a weighted ladder climb. And so this ladder on the right here, it's a 1.1 meters long. It's about 80 to 85 degrees away from the vertical. So it's almost vertical. And the rats are placed at the bottom with a bag of weights attached to their tail, and they're encouraged to climb to the top. So the rats had the weight attached to their tail. They were placed on the bottom, and they would climb to the top of the ladder. The rats initially started with a load based on their body mass, and then if they're able to make a climb successfully, we then increase the load. If they have to make that climb successfully, we increase the load again and again and again. So once they had the maximum training load for their first day, the next successive days were 50%, 70%, 90%, and 100% of the previous load. And if they're successful with all 4 climbs, we would then add 30 grams, and they'd continue to climb at heavier and heavier and heavier until failure. And so every single time they trained, they always trained until failure. And they did that resulted in 5 to 10 climbs per day. And they would train 3 days per week. And again, always until failure. And then the combination exercise group performed a combination of both treadmill and ladder climbing. So they did the treadmill 3 days per week, so Monday, Wednesday, Friday, and ladder climbing interspersed on Tuesday and Thursday. All training lasts 12 weeks. At the end of the 12 weeks, all animals performed the maximal treadmill test. So the animals were placed on the treadmill. The back of the treadmill had a shocker grid. So if the animal came off the back of the treadmill, they would then there'd be a small shock to their feet. So a deterrent to getting off the back. And so the animals were placed on the treadmill and they ran at increasing speeds. So initially the speed was increased by 1 meter per minute every 2 minutes. And after 10 minutes, it was then increased 2 meters per minute every 3 minutes. And we measured until the animals couldn't keep up with the belt, or they fell off onto the shocker too many times in a minute. For the maximum strength, so to compare these strength adaptations, we compared the maximum load the animals are able to carry each week. Because the animals always climbed until failure, their maximum load was constantly changing, and so we just compared how much they're able to carry over the course of the training protocol. For the structural measures, we use echocardiography to determine. The two we looked at in particular were the ventricular volume, or the size of the ventricle, and then the wall thickness of the ventricle. And so to get a ventricular volume, we would take views in two planes. So the first plane is the 4-chamber view. So here you can see the big chamber there is the left ventricle. Above that is the left atria. And then the smaller chamber is the right ventricle and the right atria. And if you look carefully between the left and right atria, you can see the aorta coming off to the side. And so here we're able to see all 4 chambers. We then took a almost perpendicular view through the left ventricle and left atria, so only the 2 chambers, and it gave us this image like this. So here you can see there's the left ventricle is the bigger chamber and the left atria. So now for the left ventricle, we have in 2 planes of view, we have the internal and external diameter of the vessel itself, or the chamber itself. So we trace the inside on the 4-chamber view, trace the inside on the 2-chamber view, and then to get the area of the heart. And then with the 2 planes, using the area, the Simpson biplane method, we were able to calculate the estimated ventricular volume. For the wall thickness, we then did similar to the 4-chamber view. So again, on the top, you can see that big chamber is the ventricle, and the aorta is coming off to the side. Here we get a fixed point on the wall, and over time, we'd measure the movement of that wall in and out. So on the bottom, you can see in the plane where the green line is, over time, where the position of the chamber is moving in and out. So each of those waves essentially is a contraction of the heart muscle. And so we measured the wall thickness as the area of the wall that was moving in and out. Once exercise training was done, the hearts are removed and weighed, and the trabeculae muscle lining the inside of the left ventricle was chemically dissected and then chemically skinned to enable mechanical testing. Like in the previous studies, the muscle was set between a length controller and a force transducer. So on one end, we have the length controller, which allows us to control the length and ultimately the amount of stretch or the sarcomere length of the muscle sample. And on the right, we have the force transducer, which measured the instantaneous force response of the muscle itselse. In all our experiments, we controlled for the sarcomere length of the sample, as well as the temperature effects that might have occurred. So in the mechanical testing itself, we looked at the active force production, the shortening velocity, and the sensitivity of the muscle to calcium. So I'll talk in detail how we actually measured those things. And so here's going to be a force trace of the measurement itself. The top is going to be the force, kilonewtons per meter squared, so that's stress. So force normalized to the cross-sectional area of each sample. And on the bottom, we have the length of the sample, just in percent fiber lengths. So initially, the sample was transferred to a bath that contained both ATP and calcium, and the introduction of calcium and ATP allowed the muscle to contract. And so length was held constant. It was an isometric contraction. And then we simply measured how much force was able to be produced, the maximum active force that the muscle was able to produce isometrically. Once that was obtained, we then induced a very rapid shortening. And so the sample was shortened, in this case, by 10% of its fiber length. And that very, very rapid shortening results in a very large drop in force. It was then re-lengthened and ultimately deactivated, which caused the force to return back to 0. So if we zoom in on that very rapid shortening, we get a trace kind of like this. So this is, in this case, the force at the very top is isometric. It then drops to 0 and then slowly redevelops. And so as the sample is rapidly shortened, it goes slack. and we get a trace that looks like this. So in this image here, there's three distinct phases. So initially, we have the maximum isometric contraction. And so the muscle is held at a constant length. It's, in this case, fully active, and we get the maximum active force. The sample then undergoes a very, very rapid change in length, and the muscle is still fully activated, but the length of the muscle shortens so rapidly, the sample becomes slack. So the sample is now slack, and then because the muscle is still active, it continues to shorten over that distance, and we then get force redevelopment. And so because we know how far we shortened the muscle, which by 10% its fiber length, we then measure the time it takes until force redevelops, so that the time it takes for the muscle to shorten across the gap we created, and that allows us to determine the shortening velocity under zero load, or the maximum unloaded shortening velocity. The next test, looking at calcium sensitivity. So now we have force on the y-axis and then time on the x-axis. And so for determining calcium sensitivity, we simply transfer the muscle through increasing concentrations of calcium. And so initially it starts at a low concentration, and it progressively increases through different increasing concentrations of calcium. And so each of the vertical lines is just a noise from the system physically moving past, and then the increase in force is developing as the concentration of calcium increases. So we then take the force output normalized to 100% force output for each calcium concentration. That is plotted here. So on the y-axis now we have the relative force, all normalized to the maximum force output, which is the point on the top, very top right. On the x-axis, we have the calcium concentration. So for PCA, the lower the number means the greater the calcium concentration. And so as you can see, with increasing calcium concentrations, we saw it increase stepwise in the force that was being produced. To quantify this relationship, we take the 50% of relative maximum force, and we determine what calcium concentration results in that. And so this is the calcium concentration that results in 50% maximum force, and we term it PCA 50. It's just the way we quantify the sensitivity of the muscle to calcium. So now for the results. So again, we did a maximum treadmill test, and this was an indicator of maximum aerobic performance. And so on the y-axis, we have the time it took till exhaustion, so until the animals were unable to keep up with the pace of the belt, or they were unwilling to continue. And then the four groups along the bottom. And so, unsurprisingly, when we compare the aerobic to control groups, the aerobic trained animals were able to run for a longer duration than the control animals. There was no difference between the resistance trained and the control animals. So those who did not participate in aerobic exercise did not adapt aerobically. And then the combination animals adapted in a similar manner as the aerobic animals. So any animal who participated in aerobic exercise of any kind had a greater time to exhaustion compared to the control animals who were sedentary. When we compared the maximum load carried, so now on the y-axis we have the maximum weekly load, and this is in percent to the normalized to the initial load the animal was able to carry. So on the y-axis, we at the very bottom we have the first load they're carried, and then the percent increase that they were able to lift. And the bottom, on the x-axis, we have the weeks from 1 to 11. In this case, we only have data for the resistance and combination trained animals because the other animals didn't perform resistance training, so we don't have their maximum loads carried. For the resistance trained animals, we saw an increase of close to 2.5 times, so they increased progressively over the course of the program. And the combination animals, again, increased at a similar rate. So both trained groups increased in their weekly load, and there was no significant difference between the resistance and the combination trained animals. For the structural adaptation based on echocardiography, now on the y-axis we have the ventricular and diastolic volume, and the x-axis we have the groups. So when we compare the volume of the hearts, both the aerobic and combination animals had greater volumes compared to the control animals. So the aerobic exercise training led to greater volume, whereas the resistance exercise training did not. So the animals in the resistance group had similar ventricular volumes as the control animals. For the left ventricular wall thickness, now on the y-axis, there is an increase, there's greater wall thickness in the aerobic compared to the control group animals. There's similarly an increase or a greater wall thickness in the resistance compared to the control animals. And then also an increase in the combination over the control, though this was by magnitude a little bit smaller. When we compare the active force now on the y-axis, again, this is active force normalized to the cross-sectional area of each sample. There is no difference in the active stress that's produced between the aerobic or the control animal parts. However, there is an increase in the active force production of the resistance and the combination group animals. And so the maximum force output of the muscle was greater in the animals who performed resistance exercise training. For shortening velocity, now for shortening velocity, we normalized the fiber length. So this is fiber lengths per second. We saw an increase, or we saw greater shortening velocity in the aerobic animals compared to the controls, and similarly in the resistance and combination trained animals. So all animals who participated in any kind of exercise had a greater the muscle had a greater shortening velocity compared to the control group animals. When compared calcium sensitivity, we saw increases in calcium sensitivity in both the aerobic and resistance trained animals. However, there was no difference between the combination trained animals and the control. And so calcium sensitivity was greater in either the aerobic or resistance trained animals, but when combination did not lead to that same improvement in sensitivity to calcium. And so, like previous studies, we replicated the findings that with resistance training, we see an increase in wall thickness, no change in the volume. With aerobic training, we see an increase in both wall thickness and ventricular volume. With aerobic exercise, we then repeated the results that there's no change in active force, an increase in shortening velocity, and an increase in calcium sensitivity. And so this is in support of the previous findings from the literature. For the first time in this study, we also identified that resistance training leads to an increase in active force, increase in shortening velocity, and an increase in the sensitivity of the muscle to calcium. In the combined group, we saw increases in both the wall thickness and the ventricular volume. We saw an increase in the active force production, increase in shortening velocity, but there is no change in the sensitivity of the muscle to calcium. And so, generally speaking, all exercise led to improvements in both the structural and mechanical adaptations. However, the specific adaptations to resistance training and aerobic training were somewhat different. And so we compare those results to the two background studies I talked about with obesity. We see very distinct differences in the way the muscle adapts. And so with obesity, we see decreases in the shortening velocity, whereas with exercise, we tend to see increases in shortening velocity. And then with obesity, we tend to see decreases in sensitivity to calcium. With exercise, we tend to see increases in the sensitivity to calcium. So very distinct differences in the adaptation to obesity versus exercise. And so the next question we wanted to evaluate was how the muscle will adapt if exposed to both concurrently. And so if we have animals who are exposed to obesogenic diet and participating in different forms of exercise. And so the second study I'll talk about compared the effects of obesity and exercise. And so we compared with 3-month-old Sprague Dawley rats, the impact of both aerobic and resistance training in combination with high-fat and high-sucrose diets. And so for this diets, we use the same as previously described. The chow diet was the same as the chow diet previously, and the same high-fat, high-sucrose diet, which contained higher amounts of fat, and the carbohydrates were sourced from sucrose. In this study, we compared the same groups as previously. So we compared the chow diet sedentary from the previous study, the chow diet aerobic from the previous study, and the chow diet resistance exercise group from the previous study. We also then added a high-fat, high-sucrose diet aerobic and a high-fat, high-sucrose diet with resistance exercise training. And these animals all participated in 12 weeks of exercise. So all the same mechanical measures: active force, shortening velocity, calcium sensitivity. In this figure now we have the active force on the y-axis. This is active force normalized again to cross-sectional area. And on the x, we have all the groups of animals. So when we compare active force, As I mentioned in the previous study, there's no difference between the aerobic exercise and sedentary animals who consume the chow diet. However, there's an increase in the resistance training animals active force. When we compared the impact of the high-fat, high-sucrose diet with aerobic exercise, there is no change between the active force between the aerobic exercise groups, whether or not they consume the chow diet or the high-fat, high-sucrose diet. And for the resistance trained animals, both the chow diet and the high-fat, high-sucrose diet animals adapted with an increase in the active stress production, and there's no difference between the two diet groups. So overall, the resistance training led to an increase in the active force production, and in this case, the high-fat, high-sucrose versus the chow diet had no overall impact. For shortening velocity, again on the y-axis in 5 lengths per second, when we compared the chow and sedentary animals to the chow aerobic and chow resistance animals, there's an increase in the shortening velocity, as we previously discussed in the past slides. When we then looked at the impact of the high-fat, high-sucrose diets, we saw a diminished response with the high-fat, high-sucrose diet in comparison to the chow diet. And so the animals who consumed the high-fat, high-sucrose diet but performed the same amount of exercise as the chow diet did not adapt in the same way. So shortening velocity was inhibited. And similar with the resistant trained animals. So the animals who consumed the high-fat, high-sucrose diet did not adapt in the same way despite the same training load as the animals who consumed the chow diet. So overall, in both cases, the high-fat, high-sucrose diet inhibited the adaptation to shortening velocity that we're seeing with resistance and aerobic exercise training. When we compare calcium sensitivity, again from the previous study, the aerobic and resistant exercise animals both had increases in calcium sensitivity compared to the chow animals. And with the impact of the high-fat, high-sucrose diet, there was a diminished response in the high-fat, high-sucrose and aerobic exercise training response, and with the resistance training response. And so calcium sensitivity adaptation was inhibited with the consumption of a high-fat, high-sucrose diet when combined with both aerobic and resistance exercise training in comparison to the chow-fed groups. And so overall, both aerobic and resistance exercise training lead to changes in active force, shortening velocity, and sensitivity, but when consumed alongside a high-fat, high-sucrose diet, with the exception of active force, those adaptations are inhibited. And so when we look at the overall effect of cardiac function, obesity leads to decreased function, largely due, we think, to those mechanical properties. Exercise training, both aerobic and resistance, lead to increased function, both a combination of structural and functional outcomes. But the combination of the high-fat, high-sucrose diet and obesity with aerobic and resistance exercise training inhibit the adaptations of both. So from one perspective, performance of exercise prevents the decreases in function, as seen with obesity. And the other side of things, a poor diet inhibits the adaptations of the heart muscle in response to exercise. And so I certainly have lots of people to thank. I have lots of collaborators I work with both in these studies and generally in my time at the University of Calgary, lots of funding agencies. So certainly very, very appreciative of everybody who contributed. Like Emily mentioned, my book came out about a month and a half ago. So my book is available if anyone's interested in mechanisms of super strength, super speed, teleportation, super healing. You might find this book interesting. It's available broadly through different retailers, and there's more information on that website. And so I'll leave the slide here. I'm happy to answer any questions.
Thank you, Kevin. Great. At this time, if you're comfortable, I would please encourage you to turn on your camera, as it may allow for a better discussion. To ask a question, you can use the raise hand function, which is located under reactions on the bottom of your Zoom screen. And if you are unable to use the raise hand function, you're welcome to type your question in the chat box and I will read it aloud. So Amin, thanks for starting us off. Would you like to ask your question, please?
Sure. Thank you, Kevin, for your presentation. I was wondering if you noticed any change in the behavior of the rats in the control and exercise group in terms of the amount of activity that they do during the day?
Yeah, it's a good question. We didn't measure those things. Certainly, when they finished exercise, they appeared tired. In a previous study, we looked at different doses of aerobic exercise, and in that case, we had lasers that span the cage, and so when the animal moved around the cage, they broke the laser beams, and so we tracked number of beam breaks per time, and so whether or not the animals in that case performed 30 minutes 5 days a week, 60 minutes 5 days a week, or 60 minutes 7 days a week, their sort of around the cage activity was generally unaffected. So the amount of time they did like grooming type behaviors versus like traveling around behaviors, neither of those were affected by, at least with aerobic exercise.
Matt, please ask your question.
Sorry, I'm still not sure about that.
Can you guys hear me okay? Yeah, thanks, Kevin. That was great. Good to see you again, and really enjoyed the talk. Just maybe a bit of a naive question. I can kind of wrap my head around the hard adaptations that you presented here today from a kind of health standpoint. What's the relevance of shortening velocity? Like from a heart health standpoint, what would be the clinical piece of that? And I'm just curious, you wouldn't mind just describing a little bit like how you measured it? Was it a maximum shortening velocity? I'm just kind of curious about what you did there.
Yeah, so it was maximum shortening velocity, and so we used a slack test, and so the sample is shortened so fast that the sample actually becomes slack, and so the time it takes to shorten that distance, we use to determine the velocity. And so when it's actually shortening, there's no load; it's just shortening to become not slack, so going from slack to taut. And so in that case, it's a very maximum loading or shortening velocity. The reason we measure that is typically the power output of the muscle is relevant for contraction. And so if the muscle is able to shorten at a high force, at a high rate, it's able to produce a higher power. And so we kind of measured the opposite ends of the force velocity relationship. We measured maximum isometric force and then maximum shortening velocity. And then the idea there being that in between, you'd have a greater power output at any given point.
And do you have a thought on, like, again, I'm thinking about kind of heart health, and I'm thinking about always sort of like, where does the extension go? I obviously get around the ventricular adaptations and a thicker wall and a bigger ventricle, but you have presumably a heart that has better power or higher velocity of shortening, which I guess in the middle, if you had that whole thing shifted up, you'd assume the whole thing was generating more power broadly, but how would that play into cardiac health? And I know it's a naive question, and I'm just really curious about that.
Yeah, it's a good question. I guess if that force velocity relationship does shift up and right, then for any given velocity that it has to shorten at, it can do so at a lower force output to get the same power. So either you have at the very high end of function, you have a more power to produce the ejection you need, or at a sub-maximal range, you can do that same shortening with a lower force output or a lower overall velocity.
Thanks.
Brent, please go ahead.
Can you hear me?
Yeah.
Okay. First of all, I applaud you for doing that with your daughter in the background the whole time.
Yeah, so
you didn't skip a beat. No, that was awesome.
I was hoping that didn't come through.
No, it came through. She needed help, Daddy.
You wanted a cheese string.
I'm expecting some books, by the way. I mean, you're gonna make me buy one of these books?
Maybe we can make a deal.
So you show that the high fat, high sucrose diet sort of inhibits these exercise gains. What about other diets? What about the pizza and beer diet? What was I guess maybe that is high fat, high sucrose. I mean, it's definitely high carb and some fat. Like, what about less of a sugary diet? But I don't know, the pizza and beer diet. What would that do?
Yeah, it's a good question. I don't know. Like, I don't know. See, I don't know whether the way we did our study, we didn't. So I kind of presented that as the effects of obesity, but essentially what we measured was the effects of a high fat, high sucrose diet. And so at the end, when we did DEXA scans, the animals they did have a much higher percent body fat, but it was more so the effects of the diet itself. And so whether or not a similar diet leading to similar obesity would have the same effect, I don't know. Maybe it's something about the sucrose itself, or maybe it's something about the fat itself. That maybe a non-sucrose obese diet might not have the same effect. We did do another study looking at a high protein diet. And so we were trying to enhance the structural adaptations of the heart by having the animals run on treadmills and then also consume a whey protein supplement. And that didn't seem to have any additional benefit to the animals. So a really, really good diet didn't seem to have the same effect or any more effect. But I don't know what other, say, bad diets would do. Presumably the same thing, but I don't know for sure.
And then how bad is the bad diet? Like, I mean, are you talking about, like, it's not just somebody having McDonald's like once a week or twice a week, right? It's kind of every single meal is just really bad, right? I'm trying to put this in perspective for how much I can exercise and how much pizza and beer I can drink.
Yeah. So the diet itself, it's essentially like, it'd be like shortbread dough without water. Like it feels like just like fat and sugar and flour. Like it's very. It'd be like eating McDonald's like every single meal. So I guess to numbers, the control animals are typically around 20% body fat. The aerobic trained were typically around 10, resistance trained were around 15, and then the obese diet ones were around 30. And so they'd have between 20, so sedentary would be 20%, high fat sucrose would be sedentary would be 30%. So it's a much higher percent body fat. So I guess that would be a relatively good indicator of probably what your question is looking at.
Okay, no, that's helpful. And then really quickly, and I'm sorry if I missed it, but Kelsey would always talk about these responders on this kind of diet, how you have some rats that get fat and other rats that don't get fat at all, but they still have all of the metabolic syndrome that the fat rats have. Do your rats do the same thing? Do some get fat and some don't get fat?
I think I was pretty lucky. All of those, so I didn't use olive Graham's rats. I didn't use all of Japanese rats. I took a sample of like a sort of random sample. I think I got lucky in that the ones I did take were pretty fat. There was a range of like how fat they got, but I think the ones I did end up getting were on the higher end of being responders.
Yeah. Okay. Thanks.
But if we did repeat it, I don't know if we get the same thing, but we got pretty, like the ones we end up using, we got pretty lucky with.
Got it. Thanks.
I have a question, Kevin. Could you provide some context for how these results translate to human hearts? Like, which of the trends would you expect to translate pretty well, and which do we have to like make limited interpretations about?
Yeah, so certainly the structural variables. So a lot of those measures have been done in humans as well. And so some of the studies like I referenced, at least for aerobic versus resistance training, those have been done in humans. And we found the same structural adaptation. So I imagine the structural would be very indicative. For the mechanical, it hasn't been looked at, especially in skin fibers, because you need a biopsy of the heart from a human that you can't do. So given comparable training loads and doses, I would expect similar mechanical, but I certainly don't know about the mechanical function adaptations. But I would expect the exercise we chose relatively similar to what you do in humans. So an hour of running 5 days a week is pretty typical of what a human could do. The ladder climbing itself, the length of the ladder, when the animal climbs from bottom to top, it's about 8 to 12 movements. And so that's meant to simulate 5 to 6 sets of 8 to 10 reps. And so again, it's a pretty similar what you do for resistance training. So given the same training load in a human, I would expect probably similar adaptations.
Are there other questions from the audience? Amin, please go ahead.
Kevin, when I look at the result, the active force in high-fat, high-sugars group actually increased, right? So it didn't decrease the active force. So it seems that those groups still have like a stronger heart, but the shortening velocity decreased. So I cannot conclude if the high-fat, high-sugars diet was beneficial for the heart function or not. Did you keep any of those animals for a longer time to see which group shows like a heart condition or which group like live longer?
Yeah, we didn't. None of them were kept longer than the study durations. Once they were trained, like each animal was a pretty high time and money investment to get them 12 weeks of exercise training. And so once they were done the study, we used all the ones we could. We didn't have any that lived to determine those things.
So in terms of heart function, what is your comment about the adding the high fat and high sugars diet? Do you think that was like a good thing, for the heart health?
So for the active force, is that what your question is?
For the function of the heart in general.
Yeah, so certainly the high fat, high sucrose generally led to decreased mechanical function. And I think that those decreases in mechanical function are some of the mechanisms that lead to like long-term health risks. And so certainly there was no real benefit for just the diet itself. When combined with resistance training, there was still an increase in the active force, but that was what we attribute that to the resistance training, not the diet.
Oh, I see. Okay.
So on the high fat, high sucrose diet itself, there is no change in active force. It was only when it was combined with resistance training that we saw an increase in the force.
Yeah, that's right. Okay. So after like McDonald's sandwich, if you go for running, you should be good.
That's right. Running's never bad. Well, I won't say that.
Are there other questions from the audience? I have one more question, Kevin. Can you share maybe a favorite anecdote or section of your book?
Yeah, I quite like the obviously muscle is my area of expertise. So I quite like the super strength and super speed chapters. The bionic chapter might be appealing to the biomechanics people. And I also quite enjoyed at least writing the super healing section. So those are probably my favorite chapters.
Are there any other questions from the audience? Great. So with that, please join me in thanking Dr. Kevin Boldt again for his presentation today. Next week, we'll be hearing from Brian Yu, who will be presenting on the vastus lateralis force-length relationship in trained speed skaters. So I hope to see everyone again next week, and thank you again for your presentation today, Kevin.